Welcome to this video series where I'm going to talk about content contained in the book Introduction to Nonlinear Control. So this book is published by Princeton University Press and appeared in 2023. It was written by Chris Kellett and myself. And in this video series I want to go through snippets of content contained in the book, focusing on the different chapters and highlighting some of the content that then hopefully motivates further reading in individual chapters. Okay, how is this book divided? Well, it consists of 3 parts: dynamical systems, where we analyze properties of dynamical systems or equilibria of dynamical systems. The second part focuses on different methods used as controller designs. And then the third part is on observers and estimation, meaning recovering state information based on measured output data. I want to highlight 3 other books published by Princeton University Press. There are, of course, other very good books on dynamical systems and control theory out there, but here I want to keep it brief and just mention these 3 other books: Feedback Systems, Linear System Theory, predominantly focusing on linear systems, then Introduction to Nonlinear Control, providing an overview of methods used in the context of nonlinear dynamical systems, and then requiring some basic knowledge on linear system theory, although we go through some methods for linear systems as well. And then the book Nonlinear Dynamical Systems and Control, the last one on the right, goes a bit deeper than the Introduction to Nonlinear Control into several chapters, gives more general results, but also has a slightly different focus in terms of the selection of topics covered. So I recommend all of these books, but I will focus, of course, on the content in the book Introduction to Nonlinear Control. Okay, what are we looking at? What are the objects we are considering in the book? We look at dynamical systems defined as a signal x evolving in time, and the time derivative x dot can then be represented as a function f of x, in general a known or unknown function depending on the state. And we use the shorthand notation x dot to describe the derivative with respect to time. We usually omit the explicit dependence on t, but always keep in mind that x is a function of time. The right-hand side here might be just a function of x, but it might also depend on t, or the other part we focus on an input signal u, so might be depending on u here. And then the general question we will be asking and answering in the book is, under which conditions can we guarantee convergence to a particular point? So when is x of t converging to an x star for all initial conditions, or for a subset of initial conditions if we let t go to infinity? That will be made more precise in terms of asymptotic stability, and this reflects the setting for our system without input here. In the case of a system with input, the general question will be, well, how can we select an appropriate input signal, u of x, So in general, we will be looking for feedback law u of x instead of u of t, such that then again convergence of the solution of our dynamical system converges to x star. And the main method that is, or one of the main methods used in nonlinear control theory is usually relying on some kind of Lyapunov argument or Lyapunov function, which date back more than 100 years ago, the development of the fundamentals of these methods, and which really appear in various results and in the main part of the chapters covered here. So the basic idea is as follows. We want to find a positive function v, so going from Rn, where n is the dimension of the state x, to the positive real numbers. And now if we evaluate the solution of our dynamical system here along our Lyapunov function, then that should be decreasing. So kind of representing some type of energy, and the energy should be decreasing. If that's the case, then we can conclude that our state x of t is converging to x star. And why is that helpful? Well, it is helpful because we can write the derivative with respect to time of this function v as the product of the gradient of v times the right-hand side f. Meaning, this expression here does not depend on the explicit knowledge of the solution x of t, and it only relies on the knowledge of the function v and, of course, our function f, which is our known system dynamic. Well, often it is not easy to find such a Lyapunov function, but it is in general easier than finding an explicit expression for the solution. So, wrapping up, we will be looking at different applications of these Lyapunov methods, Lyapunov functions, and their applications in nonlinear control. And this idea of a decrease of a Lyapunov function will be revisited in almost all of the chapters from 1 to 18 in the following lectures. And I'm going to stop here, and then we'll start presenting content contained in the book, starting by chapter 1 to chapter